In this video, I'm going to discuss the question which appear in thermal and statistical physics in JEST 2020 examination. So let's continue with the first problem. The statement is, a rod consists of two equal sections of length L, each with coefficient of thermal conductivity K1 and K2 respectively. Okay, one end of the rod is kept at fixed temperature T1 while the other end at temperature T2 such that T1 is greater than T2. If K2 is twice the value of K1, then the temperature at the interface is how much? Okay, so here we are given a situation, one full rod of length 2L, okay, and it's divided into two parts where the first part of length L, it is having thermal conductivity K1 and the second part is having thermal conductivity K2. Okay, now if we assume that in a steady state, let's say the temperature at the interface, that is T. Okay, and also we will assume that cross-sectional area, because rod as given in the situation, we assume that let A be the cross-section, okay, of the rod. Okay, so in that case it's also given that T1 it's larger than T2, T1 is greater than T2. That's the first information that is given to us, and also K2 it is twice the value of K1. Okay, now as we have assumed the temperature at the interface, that is T. Okay, so this is what that we will obtain at steady state condition. Okay, so because both of these two rods they form a series connection, so the same heat current will flow across the interface. Okay, so it's an important point to note, because rods form a series connection same heat will flow, or same heat, or you can say same heat current will flow across the interface, flow across interface. So that means in steady state what we can do is we can compare the heat flow across the rod, across the left rod, and that will be equal to the heat flow across the rod on the right hand side. Okay, so now we must have an idea about the heat current that can flow across a slab. So let's assume a slab. Suppose this is a slab, and a certain temperature difference is maintained across its faces, and we assume that, let's assume that A is the cross section area of this slab. Okay, and if we assume that the temperature difference between these two faces, I mean the face on the left hand side and on the right hand side, the temperature difference, that is d theta. It's not dk, but it's a d theta. That's the temperature difference between these two faces. Okay, and let's assume that the thickness of this slab, that is dx. Okay, so and we also assume that the thermal conductivity of this rod, that is K. Okay, so in that case the heat that is flowing through this slab, that is d theta, sorry, heat current dq by dt, heat flowing per second, that's the heat flow or the heat current, that is equal to K, that's a constant of proportionality which is called as thermal conductivity, and then it's also connected with the area, it's directly proportional to area, and then it's proportional to the temperature difference between two faces, which is d theta, and then divided by the thickness dx. Okay, so let's call this as equation 1. So now what we are going to do is we are going to apply the equation 1 to the left rod as well as to the rod on the right hand side, and then at the interface we will compare those two equations. Okay, so for the left part, the heat current is given by the heat current, that is dq1 upon dt with small t, it's the time here. Okay, that's a heat flowing per unit time. So that is equal to, now we will apply equation 1 here. That's the K1, coefficient of thermal conductivity for the left part of the rod, and then the, let's say A1 is the cross section area and divided by length of rod L1. So I am replacing dx with L1 here. Okay, and then d theta. So d theta is what? That is the temperature difference between two phases. So here this end, it is at temperature T1, and this the temperature at the interface. We have considered this to be T. Okay, so because T1 is greater than T, so therefore this will be equal to T1 minus T. So let's call this as equation 2. Similarly, we can write the identical equation for the right part of the rod. So that means the heat current dQ2, this is Q, please note it, upon dt, that is equal to the coefficient of thermal conductivity for the rod, the cross section area, and then thickness of the rod, which is L2, and then d theta. D theta here mean what? Because T, it's going to be larger than T2, so T minus T2. Okay, this is d theta basically. Okay, so 3. But now at the interface, because these two rods, they form a series connection, so same amount of heat will flow. Okay, so that means whatever amount of heat is flowing across the rod L1, the same amount of heat will be flowing across rod L2 at the exactly at the interface. So therefore equating equation 2 and 3, so that means in a steady state dQ1 upon dt, that will be equal to dQ2 upon dt. So that means K1 A1 upon L1 into T1 minus T, that is equal to K2 A2 upon L2 into T minus T2. But note that L1 is equal to L2, that is equal to L, so that will cancel. A1 is equal to A2, that is equal to A, because the cross section area is same for the both rods, so they will cancel with each other. And further, it's given that K2 is equal to twice the value of K1. So with this the equation reduces to K1 into T1 minus T, that is equal to twice K1 into T minus T2. Okay, so after doing the calculation, so we will notice that T1 minus T, that is equal to twice T minus twice T2, and upon solving, this will give you 3T, that is equal to T1 plus 2T2, giving the temperature at the interface, that is equal to T1 plus 2T2 divided by 3. Okay, so therefore our final answer is T1 plus 2T2 plus divided by 3. Therefore option C is the correct one here. So let's continue with the next problem. The statement is, consider an ideal gas whose entropy is given by the expression where N is the number of moles, sigma is the constant, R is the universal gas constant, U is the internal energy, and V is the volume of the gas. The specific heat at constant pressure is given by. Okay, so first of all, it's important to understand that how we can evaluate the specific heat, because we are given the information about the entropy. Okay, so here we are going to imply a relationship that connects temperature with the entropy, and from there we will be able to obtain a relationship connecting internal energy and temperature. Okay, so let's see how we can do that. So the relationship that connect temperature with the entropy, that is 1 by T, that is equal to ds by dE or ds by du, because here U is used for the internal energy. So this expression, okay, so expression for the entropy is given to us, so we will differentiate the given expression for the entropy with respect to U, so then we will obtain, so this is equal to, because we have to differentiate with respect to U and keeping all other variables as constant. Okay, so that means only this, the second term in the middle, that's only going to contribute here in this expression. Okay, so this is equal to N by 2 and then inside the bracket 5r as it is, and then curly u of ln u by n. Okay, so only this term will contribute, because the rest of the terms they will be treated as constant and they will contribute 0 in the differential. Okay, so that means this is equal to n by 2 into 5r, and then its differential, so that means 1 by x, so that means this is equal to 1 divided by u by n, and then again differential of the u by n with respect to u, so that will give you 1 by n. Okay, and that's it. So this n will cancel with this n, and then we will be left with this is equal to 5 by 2 n r, and then divided by u. So rearranging this expression, we obtain that u, that is equal to 5 by 2 n r t. Okay, so we have obtained a relationship that connects the internal energy with the temperature, and from here this implies that Cv, that is equal to du by dt. Okay, so from here we can obtain the expression for the Cv, that's the heat capacity at constant volume, and that turns out to be equal to 5 by 2 nr, and therefore Cp will be Cb plus nr, so that is 5 by 2 nr plus nr, so that is Cp is 7 by 2 nr. So therefore the specific heat at constant pressure, so that means this is the correct answer. Option B is the correct one here. So let's take a look at the next problem. So we are given a statement where a system of two particles at temperature T approaching infinity. Okay, each of them can occupy three different quantum energy level having energy 0, E and 2E. So let's try to draw the energy levels for the given system. So the corresponding energy value are 0, E and 2E. Okay, and both of them cannot occupy the same energy level, and it's given that we are having n is equal to 2 particles and they cannot occupy the same energy level, so that means they are bound to be in different energy states. So let's first draw the corresponding microstates, so you can say, or the configuration. Okay, so suppose we are having two particles A, we can call them different also, because it's given that they cannot occupy the same state. Okay, A and B, and then this could be the second scenario, and the last one could be this one. Okay, so it's better, let's call them as A and A. Okay, so now the energy for this first microstate, this is 0 for this particle and E for this particle. Okay, so that means E, and here 0 plus 2E, so 2E for this configuration and E plus 2E, that is for this third case the total energy will be 3E. So therefore the corresponding partition function will be Z, that is exponential minus beta, and the corresponding energy, that is E plus exponential minus beta corresponding energy 2E, so that is exponential minus 2 beta E plus exponential minus 3 beta E. Okay, now from here we can calculate the average energy, because we have to evaluate the average energy corresponding to the condition that T approaches infinity. Okay, so by making use of the partition function, we can evaluate the average energy as E, that is equal to minus curly beta of logarithmic of Z. Okay, so that is equal to minus curly beta of logarithmic of exponential minus beta E plus exponential minus 2 beta E plus exponential minus 3 beta E. Okay, so its differential is given by E, that is equal to minus 1 upon Z, that is exponential minus beta E plus exponential minus 2 beta E plus exponential minus 3 beta E, that's 1 by Z, and then again the differential of the exponent. Okay, so multiply by exponential minus beta E, and then again differential with respect to beta, that will give you minus E, plus the second term exponential minus 2 beta E and multiply by minus 2E, and then plus the third term exponential minus 3 beta E multiply by minus 3E. Okay, so this upon rearranging all the terms, we obtain the average energy as, so this is equal to, okay, we can take E outside. Okay, so here we are having a negative sign here in each term and the one negative sign here. Okay, so negative will become positive, so I'm taking E outside, E, and then multiply by exponential minus E by kt, beta E, that is E by kt, plus 3 the second term, okay, or 3 or 2 you can say, plus 2 exponential minus 2 E by kt plus 3 exponential minus 3 E by kt divided by the partition function, which is exponential minus E by kt plus exponential minus 2E by kt plus exponential minus 3E by kt. So now we are having a general expression for the average energy. So let's call this as equation 2. Now we are going to apply the condition, and the condition is that when t goes to infinity, so that is when t is acquiring a very large value, so in this approximation all the exponent, that is E by kt, okay, and minus 2E by kt as well as minus 3E by kt, all of these they will approach a value 0. So under this approximation we can write the average energy of the system as, because exponent is 0, so exponential will be unity. Okay, so E, and the first term this will contribute 1, and then 2 into 1 plus 3 into 1 divided by 1 plus 1 plus 1. Okay, so upon solving you will obtain that this is equal to 2E. So therefore option C is the correct option here. Okay, let's take a look at the next problem. The statement is, consider a classical harmonic oscillator in thermal equilibrium at temperature T. So that means the temperature doesn't change. Okay, if the spring constant is changed to twice its value, so it's a spring constant is changing twice to its value isothermally. Okay, then the amount of work done on the system is how much? Okay, so we know that when the spring constant is changed, so that means it's subject to a change in length. Okay, so or in other word, what we can say is that when the length of the spring is changed, its spring constant that also changes. Okay, so in simple word, according to the given situation in the problem, because the spring constant it's changing from k to 2k, or in another word what we can say is that its length is changed from x to x by 2 if x is the equilibrium length. Okay, by making the half its initial length, its spring constant it become doubled. Okay, so that means when you are so this is only possible when we are compressing the spring, or so that means we are changing the potential energy of the spring. Okay, because of the potential energy that's proportional to half kx square, and this is the change in potential energy which is stored as the work done on changing its length basically. Okay, so therefore the work done during this process is stored as potential energy in the spring. Okay, and also note that the temperature during this entire process, temperature doesn't change. because we are going to make use of this fact in solving the problem, because the constant temperature that will allow us to find the energy associated with the degree of freedom. So let's see how we can do that. So that means the work done during this process, that is equal to, so when you are changing the spin constant from k to 2k, and then that is equal to 1 by 2 dk, because it's a spin constant about which we are talking about, which is changing dk, and then the corresponding displacement. Okay, so let's call this as equation 1. Okay, so now according to Virial theorem, when a particle is subject to a potential of the form b x power n, okay, so in that case the relationship that holds between the kinetic energy, the average kinetic energy and the average potential energy, that is average kinetic energy, that is equal to n by 2 and then average potential energy. Okay, so here for the given situation here n is equal to 2, so that means when we put n is equal to 2 here, the average kinetic energy that become equal to average potential energy. So this situation is valid here in the current situation, so that means average kinetic energy that is equal to average potential energy here. Okay, and further, so this is the result 2, and further the total energy can be written as the sum of the kinetic energy plus potential energy, or this is equal to twice the potential energy for the present situation. Okay, and the average value of the potential energy, that is equal to 2 times 1 by 2 k and average value of x square. So here either we can talk about changing the value of x, or we can talk about changing the value of k. It's a mean, because the change in one is reflected as a change in the other quantity. Okay, so here note that k is the spring constant here. Okay, but also, so let's call this as equation 3. If we just take a look at the Hamiltonian for the spring, okay, so it consists of two terms, p square by 2m. It's for the one-dimensional oscillator, that's the kinetic energy plus the potential energy term. Okay, because temperature is held fixed, T is fixed. Okay, so that means the average energy can be written as kBT by 2, the contribution from here according to the equipartition theorem, and another kBT by 2, the contribution, the average energy, average potential energy, and their sum is equal to kBT. Okay, so let's call this as equation 4. So combining equation 3 and equation 4, so we can equate kBT, that is equal to k times average of x square, because we were interested in this obtaining the x square in terms of Boltzmann constant and in terms of spring constant. So here we are going to replace this average value of x square in equation 1, so that the work done come out to be equal to 1 by 2, and then changing the spring constant from k to 2k, and then this value the value of x square basically, that is, so from here, so from equation 5, x square average, that is equal to kBT by k. So substitute this value here. Okay, so 1 by 2 outside, so dk, I'm taking it out, I will write it later, so kBT by k, that is x square and then dk. Okay, so this is equal to kBT by 2 and then dk by k, that will give you ln k when k is changing from k to 2k, and that will give you kVt by 2 ln 2k minus k, okay, minus ln k, so that is equal to ln 2k by k, which is equal to kt by 2 ln 2. So that's the final answer. So therefore option B is the correct one here. So let's take a look at the next problem. The statement is, a classical gas of n particle is kept at temperature T and is confined to move on a two-dimensional surface xy plane as shown here in this figure. Okay, if an external linear force is applied along the x direction, so it's given that an external linear force that is applied along the x direction, then the partition function of the system will be proportional to Yes, so we have to obtain the partition function for the system and its dependence on the temperature. Okay, now remember that when the force along the x direction is applied, and simultaneously we have to keep the temperature also constant. Okay, so by applying a force along one particular direction, because it's the particles, they are going through the two-dimensional motion, so when by applying the force, the equilibrium will be disturbed. Okay, so but that's going to change the temperature. The equilibrium temperature can only be maintained when some sort of restoring force also acts on the particle. Okay, so in that sense, the restoring force, that will be directed opposite to the displacement. So what we can do is, as we do in case of spring, so the restoring force, it will be directed opposite to the applied force. Okay, so that is minus kx here. So k is the constant of proportionality, and because we connect it with the potential, the force that's negative of the potential gradient, that's minus dv by dx here. Okay, so that means from here we conclude that dv by dx, that is equal to kx, and from here we can immediately calculate the sort of the potential to which the particles are subjected. So dv, that is kx dx, or from here we can calculate the sort of the potential, that is upon integration. Okay, so 1 by 2 k x square. So this is a type of the potential to which the particles are subjected basically. Okay, so now by writing the total Hamiltonian for the particles, because it's a two-dimensional motion, so the kinetic energy term will constitute two kinetic energy term, px square plus py square upon 2m, but the potential, it's only along one direction, that's k by 2 x square. Okay, so now we can easily determine the relevant partition function for one particle z1, that is equal to 1 upon h square. Okay, and then for integral. Okay, and here we will not have 4 integral in principle, we will have only 3 integral, because the potential, it's affected only along the one direction. Okay, so that means exponential minus beta h. Okay, and then dpx dpy dx. Okay, and that is equal to 1 upon h square, and then minus infinity to infinity exponential minus beta px square plus py square by 2m. So in principle we can split this into two integral, dpx dpy, and then this is multiplied by further minus infinity to infinity. Okay, and then exponential minus beta, and then k x square by 2 dx. Okay, so this is a, here we will apply the some standard integral, that's minus infinity to infinity exponential minus alpha x square dx, that is equal to under root pi by alpha. Okay, so by applying this definition here in the first part, we will have two integral, exponential minus beta px square by 2m dpx, and then exponential minus beta py square upon 2m. Okay, so it's by applying this definition, so the constant quantity here alpha in these two integral will be beta upon 2m, or you can say 2m upon 1 upon 2m kt. So that's going to the alpha. Okay, so therefore z1 will come out to equal to, z1 will be 1 upon h square, and then this under root pi by alpha will give us 2 pi m kt power 1 by 2, because we will have two such integrals, so 2 pi m kt power 2 by 2, ultimately it's 1. Okay, and then the another integral minus infinity to infinity exponential minus kx square upon 2 kbt dx. Okay, so again here we will apply the same result under root pi by alpha. So this is equal to 1 upon h square 2 pi m kbt. This is Boltzmann constant, please remember it. And then this exponential minus alpha x square again under root pi by alpha. So this will be equal to 2 pi kbt upon k, that's a spring constant, and its power 1 by 2. That's the single particle partition function, and this is proportional to t power 1 from the first term and t power 1 by 2 from the second term. So this is, so that means that is equal to t power 3 by 2 for a single particle. So for n particle, the partition function will be t power 3 by 2 and its power n. So that is t power 3n by 2. So therefore option D is the correct one here. Let's take a look at the next problem. The statement is a particle of mass m is placed in a potential well ux is equal to cx power n. Okay, so we are given a situation where a particle is subjected to potential ux c, that is equal to cx power n, where c is a constant. Okay, it's a positive constant, and n is a even positive integer. Okay, n, that's a even positive integer. So that means the particle is subjected to the harmonic potential. Harmonic potential. If the particle is in equilibrium at constant temperature, which one of the following relation between the average kinetic energy K and the potential energy U is correct? Okay, so basically this is nothing but it's a we can identify the correct answer by using Virial theorem, which says that when we are having a situation like this, when the particle is subject to this kind of potential, okay, so in that case the kinetic energy, that is here it's given the average kinetic energy, that is equal to the exponent of this x, so that is n divided by 2, and then the kinetic the potential energy u. Okay, so therefore here option C is the correct one here. So let's continue with the next problem. The statement is a particle is moving on a one-dimensional discrete lattice with lattice spacing unity. Okay, so we are given that the lattice spacing it's equal to unity or 1 unit. Okay, so that means this is basically the step size. Okay, it can move from a site to its nearest neighbor site in every 1 by 5 seconds. Okay, so it's given that t step time taken for one step, that is equal to 1 by 5 seconds. Okay, with p being the probability to move right and q is equal to 1 minus p being the probability to move left. Okay, consider that particle starts at origin at time t is equal to 0, taking p is equal to 3 by 4. So it's further given that p is equal to 3 by 4, and so therefore q is equal to 1 minus p, so that is equal to 1 by 4. So we have to calculate the variance. Okay, and it's further it's given that at t is equal to 5 into 10 power 4 second, so we have to evaluate the variance. Okay, so what is sigma, the variance in the displacement, that is equal to how much? Okay, so from here we because in order to calculate the variance, so we know that the variance in the displacement sigma x square, that is equal to 4 n pq L square. So okay, so this result we discuss in theory. Okay, when we talk about the random walk in one dimension. Okay, so here L it's given to us, P and Q they are also given to us. So we are supposed to calculate the what is the value of n, capital N. So capital N, that is equal to the total time that is t, and then divided by time taken for one step, executing one step, and that is equal to 5 into 10 power 4 second, and the time for executing one step, and this is equal to 25 into 10 power 4 steps. So this is the number of steps. Okay, so therefore the variance, that is sigma x square, which is further equal to the average of x minus mod x and its square, okay, and that is equal to 4 multiplied by n and then multiply by p into q. So that is 3 by 4 into 1 by 4 and L is equal to unity, okay. So this will cancel this, so this is equal to 3 by 4 multiplied by the value of n, which is 25 into 10 power 4. So whatever number we are getting, that is the our answer. So that's the variance basically, okay. So let's take a look at the next problem. The statement is two compartments in a cylinder with uniform cross section and total length 102 cm are separated by a sliding partition which can move but doesn't allow heat to pass across it, okay. So that means this partition, it is capable of moving freely. Further, it's given that no molecules are present in either side of the compartment, okay. So that means it's totally empty. The radiation inside each compartment is in thermal equilibrium with its wall. So that means we are having radiations inside in these two compartments, okay. The walls at the two ends of the cylinder are maintained at temperature 2000 Kelvin and 4000. It's not 1000 but it is 4000. Please note it, and this is 4000 Kelvin respectively. The sides are perfectly insulated, so it's given that there is no energy loss to a surrounding, so these are insulated. Find the location of the partition measured from the left end of the container. So let's assume that left end is situated at a distance x in equilibrium position, and so that the remaining distance on the right hand side, this is 102 minus x centimeter, okay. Now, so we can solve this problem by having the idea of what the expression for the pressure exerted by the radiations, okay. So because here the both of these two ends, they are at different temperatures, so that means the corresponding energy density at these two ends, because of the radiations, when the system is not in equilibrium, so here the energy density or the pressure exerted by the radiation, let's say it is P2 and it is P1 initially. So when, because of this pressure imbalance, because of the energy density contained in the container, okay, on these two partitions separately, so as long as there is no the balance of the pressure on the both sides, so this partition will keep on moving until we are having a situation where P1 is equal to P2, okay. Now the question is, as we learned in statistical mechanics, when a system exchange volume, okay, so then ultimately the equilibrium is established by this condition, that when the pressure is same on both sides, okay. So the pressure exerted by the radiation, we know that this is equal to 1/3 of energy density, okay, and so that means energy divided by volume here, okay. And further, it's known that the energy energy density or the energy because of the radiation, it's proportional to T power 4. Okay, so we will make use of these two facts here to figure out the exact value of x, okay. So that means for both of the partitions, when P1 equal to P2, so this is this means because power, that's pressure, that's further 1/3 of energy density, and energy is proportional to T power 4, okay. So that means T1 power 4 divided by the volume 1, okay, which is the cross sectional area multiplied by the length x, okay, and that is equal to T2 power 4 divided by the cross sectional area and multiply by 102 minus x, that's length, that will give you the volume. So when these two quantities, they will balance, then ultimately P1 will become P2, and then further this partition will stop moving, okay. So A and A will cancel with each other, so let's substitute the value of T1 and T2. So here T1 corresponds to 2000 power 4 divided by x, that is equal to 4000 power 4 divided by 102 minus x, okay. So that means 2 power 4 divided by x, that is equal to 4 power 4 divided by 102 minus x, okay. So this can be further solved as, so after cancelling the common factors, that is 1 by x, that is equal to 16 divided by 102 minus x. So this implies 102 minus x equal to 16x, and this upon further solving this 17x, that is equal to 102, and therefore it gives that x is equal to 6 centimeter. Okay, so for when this partition, this is at x is equal to 6 centimeter, so this will stop for further moving. So this is the final answer. Let's continue with the last problem. The statement is, consider a cube of volume B containing n molecules, each of mass m with uniform density n is equal to n by b. Suppose this system is equivalent to a system of m non-interacting gases such that the molecules of ith gas are Ni is equal to Niv in number, each with an integral bicomponent of velocity Bi. What is the pressure P on the surface ABCD of area A? Okay, so in order to solve this problem, as per the instructions given in the statement, so what we are going to do is we will divide these n molecules. So we are having total molecules, they are n. All of them, they are identical with the mass m and same component of velocity Bi along the, that is By, that is equal to Vi. It's same for all the gas molecule. Okay, it's given. Okay, now we will divide these gas molecule into m subgroups. Divide them into m subgroups. So that means the first subgroups, let's say it contain n1 gas molecule, second contain n2, third is having n3, and so on. Mth subgroup contain capital N m gas molecules. Okay, such that the total number of gas molecule, that is equal to sum of all these Ni, where I taking value from 1 to m. So let's call this as equation 1. Okay, so now we will talk about the group 1, which is having n1 gas molecules, each of mass m and with the respective y component of velocity Vi. Okay, so now we among these n1 gas molecule, we will talk about one single gas molecule, okay, which is moving along the y direction. Okay, so let's say this is the face ABCD. So this is the face ABCD, such that when gas molecule is moving from let's say from the extreme left, so that is at y is equal to 0. Okay, so let's say it's moving like this, and its momentum will be mvi, and when it will hit the face ABCD, it will again come back, but with the corresponding momentum, that is equal to minus mvi. Okay, so that the net momentum change delta Py for this gas molecule will be twice of mass multiplied by Vi. Okay, that's the momentum change of this gas molecule. So let's call this as equation 2. Now what is the respective time that is taken by the gas molecule to come back to the same phase, initial phase? Okay, so that is equal to the distance traveled by the gas molecule, which is 2L, and divided by the velocity with which it travel that distance, and let's call this as equation 3. So the corresponding momentum change delta P by, that is equal to, okay, sorry, now the force exerted by the gas molecule along y direction, that is F1y, that's the y single gas molecule, it's y single gas molecule, that is delta Py upon T. So that is equal to 2 m Bi upon 2L and Vi. So that is equal to, 2 will cancel with 2, so this is equal to mvi square upon L. That's the corresponding force exerted by one single gas molecule along the y direction. So let's call this as equation 4. Now we have determined the force by one single gas molecule. So from here we can determine the net force exerted by n1 gas molecule, the net force F1y, so that is equal to, just 1 second please, yes, F1y, that is equal to I taking value from 1 to n1 and then F1y single. Okay, so this way we will have n1 such terms. Okay, so that is equal to m and n1 Vi square divided by L. Okay, so that the pressure exerted by N1 such gas molecule along the bidirection P1y, that is equal to F1y upon area. Okay, area of the phase, which is equal to F1y upon L square. Okay, so that is equal to M N1 upon L cube, because L square and L, that will make L cube into Vi square. So that is equal to M N1, where N1 is equal to N1 upon L cube, okay, into Vi square. Okay, so let's call this as equation 5. So here we have made use of the result that N1 upon L cube, that is equal to N1 upon P, and that is equal to N1. That's a number density. Okay, similarly we can obtain the expression for the pressure exerted by the other gas molecule in different subgroups. Okay, so that the total pressure exerted by the all the gas molecules, so that is equal to P1y plus P2y plus P3y plus so on Pm by. Okay, and that is equal to we will make use of the expression 5 to generalize this result. So this is equal to M N1 Vi square plus M N2 Vi square, because by component same for all the gas molecule, plus so on M N M Vi square. So this is equal to, we are taking M outside, summation I taking value from 1 to M, and then Ni Vi square. So that's the expression for the pressure exerted by all the gas molecule on the phase ABCD. So let's say yes. So that means option A is the correct one here. So that completes the all the solution.